no question. Let's look at some numerical examples. Right. So here we show an amplifier. This amplifier, we have the noise due to the amplifier, but this time we put it in the input, right? And then you have the gain. We can short it so that this can all be combined together and see this thing, right? But the point is that what is the noise figure of this amplifier? Right? Based on what we learned earlier, is 1 plus Vn in square divided by 4kTRS. If you remember, it is that you transform your amplifier's noise to the input and then compare it to the source noise. That is how you get the noise figure. Okay, of course, if you want, we can also write it as is also equal if you have at the output, you put the noise at the output, then if you remember, it divided by the gain, right, of the amplifier. And then normalize to the source noise. Basically, Vn out, if we put it here, divided by alpha square A square is V in square bar. Okay, just write the equation again. So there are some numbers we want to try. For example, if the noise figure equals to 2 dB, if the noise figure equal to 2 dB, right, then what does it mean? Then it means Vn in square divided by 4kTRS equals to, maybe I should say something first here because it's a jump. What is 2 dB in ratio? So this, I call it noise figure. Actually, I should call it noise factor. This is figure. I should call it dB. Okay, so now what is the noise factor? Remember, it is 10 log noise factor equal to noise figure, right? 10 times log, right? So it is 2 divided by 10 and then to the power 10. Which is equals to 1.585. Let me erase this. I know I did not teach you smoothly. Let me say again. When we say a noise factor, figure equal to 2 dB, it means the noise figure, it means what? Noise figure in dB equal to 10 log times noise factor. Remember this? 10 log times noise factor. So it means that the noise factor equals to noise figure divided by 10, and then you take 10 to the power of it. Do you get it? Any questions for this part? And that's why when I say it is 2 dB, then it becomes 10 to the power 2 divided by 10, which is 1.585. Sometimes I may not write dB here, right? But if I give you the unit as dB, you understand it is expressed in this unit. Because not every test board or everyone will distinguish noise factor from noise figure, or they actually have different definition. But you should understand what they are talking about. If they give you a pure number, they are talking about the ratio of the signal to noise ratio in input and output. Yes, if they give you dB, then it means it's the 10 log that ratio. So now I give you 2 dB, it means the ratio of them is 1.585. It's okay? So if this is 1.585, then it means 1 plus Vn in square bar 4 kTRS equal 1.585. Right? So as a result, V in square bar equals to 0.585 times 4 kTRS. This is the noise, the power spectral density of the white noise of your amplifier is equal to this. Okay? Now you can plug in the numbers. If Rs equal to 50 ohm, right? If temperature equal to 300 Kelvin, then what will you get? Right? I already did that. The square root of this, or the the square root of this spectral power spectral density equals to 0.696 nanovolt per square root hertz. Again, we're talking power spectral density. This is not the voltage, right? So that's why it's expressed as nanovolt per hertz, which we have discussed at the beginning. So this just gives you an idea, right, how to do the calculation. Is that okay? Now let's also look at another example. You may have a wire when you route, for example, right, in your project, if you're very lousy in doing the layouts, you're lazy. You just only try to connect it one point to another point. And you use minimum width without considering other things. You may introduce a lot of resistance. Let's say this is a wire. It has a width and it's a length, right? Your signal propagates from A to B. So how do I find the resistance of this wire? So of course you can do all the calculation, but in the PDK, they usually give you something called sheet resistance. Sheet resistance. Try to see if anything is left. So what does it mean? It is R square, what we call the R square. Okay? The unit is ohm per square. What does it mean? It means if you give me, for example, let me give the example, for example, for poly, because you use it for routing, metal 1, metal 2, diffusion, they all have this so-called sheet resistance, right? The sheet resistance. So what is the total resistance? The total resistance actually equals to the sheet resistance times the L divided by W. Basically, it's just saying that this is the resistance of a square. The reason is this. This one has a certain R. If I double its width and double its length, the total resistance is also R. Do you agree? Because double its width, then you reduce the resistance by half. Double its length, you increase the resistance by another time. Right? So multiply 2 divided by 2, so you still have R. So in semiconductor circuits, we always will try to look at W, L divided by W. It's not your length that matters. It's the L divided by W that matters for your total resistance. Do you agree with me on this? And the total resistance is this characteristic resistance, because this is determined by the process, how thick they make the metal, what type of material they use to make the metal, what is the annealing temperature, what is the resistivity of the metal. Then in your semiconductor chip, if you lay out one square, then you have this, I should call this square, R square. If you make it wider, okay, I have enough area due to some reason, I make it 3 by 3. This is not 3 by 3. Then what is the resistance of the last one again? Still the same, R square. Right? I'm talking about the top view from your layout. Is this concept clear or no? I think this is important. Maybe some of you don't get what I mean. It's like this. You have source, you have drain, right? You have a gate. This is the poly. And then you route it from here to here. Right? The resistance really determined by how many square you have here. Right? So I actually only have one square. I look at the square, right? Not rectangle. 2 square, 3 square. This is a 3R square. The total resistance is 3R square. If you say I try to make this wider by 2 times, but I allow it longer, it's still 3R square. If you keep the same length, but you double it, then you reduce the total resistance by half. Understand now? Okay, so I take this opportunity to introduce the concept. Then for example, right, I can have 40 milliohm. Of sheet resistance, for example, for metal, what is this one for? I forgot what is this, but let's say this is metal 1. Yeah, should be metal 1. It means in metal 1, you do this square, you got 40 milliohm already. If you use metal 2, it might be smaller. If you use poly, it might be larger. If you use diffusion, it might be even larger for the same square, right? And then maybe my length here, let's say it is 200 micron, right? You are really lazy in the layout. You are rushing for the project. You did not minimize your area. You have 200 micron. And then your width may be, how about 0.5 micron? Then what is the total resistance here? It will be 200 divided by 0.5 times 40 milliohm, right? You do the math. This is equal to 16 ohm. So if you don't do the routing right, just the wire go into your LNA already give you 16 ohm of resistance. Now, this is not just slowing down or giving you other trouble. It generates a lot of noise. What is the noise associated with this wire, like what we're drawing here? This is RL. Maybe I just call this RL. You route it so long, you actually get a noise coming from this wire, right? What is the noise again? Can someone tell me? I mean, what is the equation for the noise? Vn. Thank you. The wire Vn wire square equals to, I actually should, 4 kT RL. Okay? If you go through the math, now there's a way you can do it fast, because I already know that 4 kT 50 ohm, this is the same, right? I'm trying to trying to do something first. RL is 16 ohm. I try to multiply by 50 divided by 50, right? It's the same, right? But I already know what is 4 kT 50 ohm. Do you remember? Anyone remember? No, for the noise, it is 0.191 nanovolts per square hertz, right? So we have square times 16 divided by 50. If you remember, right? If you don't remember, just plug in the equations. And this one gives us 0.265 times 10 to the power negative 18 volt square per hertz. Again, we're talking about power spectral density. Yeah. Is that okay? Now, so this is right. Then we add to the previous example, previous slide amplifier. What we're saying is that in the previous, we already came up with noise figure equal to 2 dB. But now I did not do the layout right. I have a very long wire. So I add additional wire to it. Okay? So what is the noise figure? It's going to be 1 plus, first is the noise figure due to the amplifier. This is from the previous slide, 4 kTRS. And then I also have the 4 kTRL that I got from this wire, right? And I already know that from the previous slide, this is 0.585 that I gave you, 0.585 for this term. But now I need to add to this one. If you do the math, it is, what is that? I did something wrong, right? I need to normalize. I'm sorry, not just 4 kTRL. What should I use in noise figure? Is it only 4 kTRL? 4 kTRL in noise figure. I need to normalize to the source noise by the definition of noise figure, right? I have the noise here of the amplifier. I normalize to the source, so divided by 4 kTRS. So I have this 4 kTRL due to the wire. I also need to normalize to the source. Okay? So this becomes just 16 divided by 50. Okay? So you go through the math is 0.32. No, the last term is 0.32. The total is 1.905. Right? The difference between this one and the last one is that I added the noise due to the wire. And if you go through the math, this equals to 2.79 dB instead of 2 dB. So here we have some math I want you to practice because you need this to do your assignment and also design your LNA in your project. You need to go through all this math and then decide what would be the noise figure and then try to do the simulation at different temperature. So let me recap one more time. Sorry, I didn't teach this well. The point is, first, pay attention to the difference between noise factor and noise figure. Really doesn't matter how you call it. I also keep messing up. The main point is that one of them is just a ratio. One is dB. The dB one is the 10 log the ratio. That's it. To convert it to ratio from dB, you use this equation. Okay? The most important is to distinguish that. Second thing is that I give these are just the numbers. What I'm using for this equation is the equation you learned earlier for noise factor already, right? So I gave you the noise factor to be 2 dB, and you find out that actually this corresponds to 1.585 noise factor, right? And then we say if you don't do the layout right, before I don't have this term. If I do the layout right, I only have the noise from the source and noise due to the LNA. This gives me 1 plus this term. But because I have the wire, now I have another noise source, 4 kTRL. Plug in, you get the ratio, which is the noise factor. take the log and multiply by 10, you get the noise figure. And it increased from 2 dB to 2.79 dB. All this here is I take the opportunity to teach you what is the square resistance, sheet resistance, and how you calculate it by looking at the PDK. It tell you what is the resistance for Fe squared. And through this, I found that for the layout that I have, I got 16 ohm. And when I know it's 16 ohm, then I get the noise generated by this resistor. That's all I want to say. Is this clear now? Cannot normalize to that because we are trying to noise figure is about signal to noise ratio. The signal actually comes before the RS. It is the RS associated with the signal. So you cannot say RL is a part of the signal, right? In that sense. But if you say, okay, I decided this part is actually the source, you can say that. Then in that case, yeah, then you will normalize to RS plus RL. But in that case, your impedance need to be tuned again, right? You either say, I do it well so that RS plus RL equal to 50 ohm. Or if not, then everything change. You just need to do recalculation. Okay? Any questions? If no, then let me